Namaskar everyone. Today let us try to understand critical load for a freestanding column. On your screen you are seeing a freestanding column. This column is experiencing a vertical load capital P. If we look at a point at distance x from the top, we can understand that this point would experience a bending moment of minus PV, where V is the deflection of this column at distance x from top. Now, let us look at the deflection equation, second order ordinary deflection equation. D square V by dx square equal to m by EI. Now in this case, d square V by dx square can be written as minus PV divided by EI. Let us take lambda square as P by EI. So this gives us deflection equation as d square V by dx square plus lambda square V equal to 0. We know that solution of this homogeneous equation is V equal to A sin lambda x plus B cos lambda x, where A and B are the arbitrary constants which have to be obtained from the boundary conditions. Please see that here the boundary conditions are that at x equal to L, deflection is 0, and also at x equal to L, slope is 0. Let us derivate the elastic curve. We get V dash equal to A lambda cos lambda x minus B lambda sin lambda x. On application of boundary conditions, we get 0 equal to bracket start A square plus B square bracket close cos lambda L. This means A square equal to minus B square. Now that is possible only and only if A equal to B equal to 0. Now this solution would be a trivial one. We will reject it and instead we will focus on cos lambda L equal to 0. So this expression that cos lambda L equal to is equal to 0 means that lambda L has to be equal to pi by 2 or 3 pi by 2 or 5 pi by 2, like that. We are interested in the lowest value of the critical load. So we will take lambda L equal to pi by 2. This gives us lambda square L square equal to pi square by 4, and substituting the value of lambda, please see lambda we had defined as lambda square equal to P by EI. So we have P critical equal to pi square EI divided by 4 L square. So you can see the critical load of a freestanding column is lower than even the critical load of a pinned column. Now let us summarize. For freestanding column, critical load is pi square EI divided by 4L square. We can write it as pi square EI divided by LE square, where LE is equal to 2L and where L is length of the column. For pinned, critical load is pi square EI divided by L square, and here in this case LE is equal to L. For fixed pinned, critical load is given by 2 pi square EI divided by L square, and here effective length L becomes 0.7 into L. And for fixed column, critical load becomes 4 pi square EI divided by L square, and the effective length becomes L by 2. So this is a standard form of expressing critical load of a column as pi square EI divided by KL whole square. Or it can also be written as pi square ei divided by le square. Now le would be equal to 2L for freestanding column would be equal to L for pinned column. LE would be equal to 0.7L for fixed pinned column. LE would be equal to L by 2 for fixed column. Now let us look at the limitations of the Euler formula of critical load. We have seen that critical load is pi square EI divided by LE square. Now let us write second moment of area as AR square, where A is area of cross section of the column and R is the radius of gyration. Now taking capital A on the left hand side, we can arrive at expression of critical stress, which is PCR divided by A, and that comes out to be pi square E divided by LE by R whole square. Now this LE by R is called slenderness ratio. Please appreciate that if slenderness ratio is large, then critical stress would be low. We want the critical stress to be large. So that means slenderness ratio should be of a column should be as low as possible. Now this is visible from this graph also, in which on the y-axis we have critical stress and on the x-axis is the slenderness ratio of a column. Also see that the curve is continuous for some part and then it is dotted. Now the curve, the continuous part corresponds to the region in which Hooke's law is valid, where stress is directly proportional to strain. And we have to appreciate that these Euler's critical load formulas are valid for this part in which these curves are continuous. That is where Hooke's law is valid, where stresses are directly proportional to strains. Now let us look at eccentric loads and the secant formula. On our screen, we are seeing a eccentrically loaded column of length L, and here there is an eccentricity of small e between the load capital P and the axis of the column. So at distance x from top of this column, we can see that the bending moment again would be equal to minus PV, where V is the deflection of the beam at distance x from top of the column. Again, we will resort to second order ordinary differential equation, which captures the deflection of this column. D square V by dx square equal to m by EI, and in this case would be equal to minus PV divided by EI. Again, let us take lambda square equal to P by EI, and if we substitute in the differential equation, we get D square V by dx square plus lambda square V equal to 0. And we know that solution of this differential equation is V equal to A sine lambda x plus B cos lambda x. And we understand that the maximum deflection of this column would occur exactly at the middle of the column at distance L by 2 from the top. So V dash L by 2 equal to 0. And V dash we can see is A lambda cos lambda x minus B lambda sine lambda x. So if we apply this boundary condition, we get, and also we apply the boundary condition that at x equal to 0, deflection is small e, right? So if we apply this boundary condition, we get capital B equal to small e and A equal to E sine lambda L by 2 divided by cos lambda L by 2. So the equation of the elastic curve becomes E sine lambda L by 2 divided by cos lambda L by 2 into sine lambda x plus E cos lambda x. This we have got when we put the values of A and B in the original equation of the elastic curve. This is the original equation of the elastic curve. V equal to A sine lambda x plus B cos lambda x. Maximum deflection would occur at x equal to L by 2, and if we substitute x equal to L by 2 in the deflection equation, in the equation of the elastic curve, we get V L by 2 equal to E bracket start sine square lambda L by 2 divided by cos lambda L by 2 plus cos lambda L by 2 bracket close. And with certain mathematical manipulations, we can find that deflection at x equal to L by 2 is equal to E secant lambda L by 2. Now let us try to find out stress which this column would experience, and we can see that this column would experience axial stress, normal stress, plus the bending stress. And the maximum value of this stress would occur at x equal to L by 2, where bending moment is maximum. So maximum stress would be equal to P divided by A plus MC by I, right? Where C is the distance of outermost part of cross section of the beam from the neutral axis, and I is the second moment of area. Here we have substituted M as equal to P into V max, and where V max is E secant delta lambda L by 2. And thereby we get sigma max equal to P by A bracket start 1 plus EC by R square secant lambda L by 2 bracket close. Or in other words, we can again write it as sigma max equal to sigma YP plus YP equal to NPA by A bracket start 1 plus EC by R square secant brackets start L by R under the root NPA by 4EA bracket close bracket close. Here we have tried to determine the condition at which this failure would occur due to yielding, and this we have done by equating maximum stress to yield point stress. And where this small n is factor of safety, we have replaced capital P by n into PA, where PA is the allowable stress, allowable load, and n is the factor of safety. Due to the presence of secant term in this formula is often called secant formula. Now let us try to look at beam columns. Beam column is a member which carries load as a beam carries, and also it carries load as a typical column carries. So beam column carries load along the axis of the beam column, and also it carries load perpendicular to the axis of the column. So here you can see a typical beam column which is pivoted at point A, and there is a spring of stiffness A, a spring of stiffness K at location A, which tries to restore the beam column to its original position, which is denoted by a dotted image. The length of the beam column is capital L, and when this beam column is deformed, the angle theta between the axis becomes the angle between the axis becomes theta, right? For this beam column, you can see if we equate all the moments about point A equal to 0, right? So we get P L sine theta plus FL cos theta minus K theta equal to 0. Right? For this is the equation for equilibrium which we are using here. So this gives P equal to K theta minus FL cos theta divided by L sine theta. Now we are dealing with small theta. When we are dealing with small theta, cos theta can be taken as 1 and sin theta can be taken equal to theta. So this gives us capital P equal to k theta minus FL divided by L theta, or theta equal to FL divided by k minus PL. Now we have two solutions for capital P. One is P equal to k theta minus FL cos theta by L sin theta. We'll call it exact solution. And another is P equal to k theta minus FL by L theta. So if we plot a graph using these two expressions, keeping on y-axis capital P and on x-axis theta, we see the graphs for exact solution and for linearized solution are as shown in this graph. You can see when theta is small, the graph of exact solution and graph of linearized solution, they overlap each other. But when theta becomes large, there is a difference between the two solutions. Also, please see that when theta becomes approaches pi, uh, exact solution gives very large value of p. Now that is understandable from this figure also. When theta becomes pi, this beam column hangs from point A, and we can understand that we can apply a very large P in this particular situation.